Hello, everybody, and welcome to this presentation. Today, we're going to talk about building an industrial serverless service and all the challenge we faced when building a serverless service for our clients at Scaleway. So let's talk a bit about Scaleway first to give you some perspective. At Scaleway, we are 400 passionate people working on the future of the cloud. We have 20 years of infrastructure experience, and we have three main brands. Scaleway Data Center to operate data centers. We build and we operate data centers. We have Scaleway Databox, where we rent high-end dedicated server. And finally, the Scaleway Element public cloud ecosystem, which we're gonna talk about today. So, why did we choose to create a serverless service at Scaleway? Usually, when you want to build a product, you have to create an infrastructure to support it. So you have to install servers, you have to install operating systems, and to maintain all this infrastructure. So for this, you need people who are specialized in this area. So it has a cost, it takes time. And today, there is a new emerging pattern, the fact that customers want to focus on code and not on that infrastructure, because it's more just a constraint than really something that you want to do. So initially, like I said, Scaleway was a IaaS-only provider, so based on the infrastructure. And recently, like 3 years ago, we created our platform as a service product line. So the idea to bring serverless at Scaleway was to expand this product line, to strengthen our position among the new kind of customers who are like developers who do not want to deal with infrastructure. And we want also to give a full range of possibility when building product to address all the different customers. So let's start with the product vision that we had. So of course, when we want to build a new product, we're trying to base it on the Scaleway stack. Yeah, that's something we really want to do because we have a full range of products. And if these products are good for you, then they are good for us. So obviously, we are based on the Scaleway stack. We also want strict isolation between users. When running the workloads, you have sensitive data, so you just want your code to be run isolated from the other users. You don't want any security or privacy breach. So this was a really strong point on which we wanted to focus. We want to use open source components. We have a strong open source culture at Scaleway. We love to use open source product and to contribute to it. So as much as we can, we try to use open source components. We want runtime compatibility with Amazon Lambda, which is one of the leader on the market of function as a service. So in order to make transition from one provider to another, then we want to do it with the much ease possible. So having compatibility with Lambda already brings you some ecosystem where you are comfortable with and like just already know it. We also want you to have the ability to bring your own containers. For function, we provide a lot of different languages, but you never know. Maybe you have something that is very specific to your domain or to your the type of work you are doing, or maybe you just want to have a bit more flexibility on the product you're building. So you have the ability to bring your own runtime by bringing your own containers. And the last point we wanted to focus on is fair deployment and cold start times. That can be translated to the developer experience, because the developer experience is key for a product adoption. So we want things to start quickly, to be fluid, to be easy to use, and to be really not fun, but very agreeable to use. So that's the product vision. Here we represented the path to readiness. So we reached the first milestone, which is the product idea. So next will be bringing a proof of concept. So where to begin? In order to create a serverless service, we need a serverless engine. So we had the first choice, right, to either we build something from scratch, and we have the ability to do it. We have a lot of developers inside the company, or to use existing software. There are several serverless engines that exist and that were available at the time, because it was like emerging, so different products. We had Knative, there was OpenFaaS, Kubeless, and such. So we had to choose. And the first thing we thought is that using existing software would give us the best time to market for our product, if it works with it. So we tried to benchmark and test a lot of different serverless engines, and we went to the conclusion that Knative was a good choice for us. It was at an early stage of its life at the time, but it was really strong with really good features. It's built to be executed in a Kubernetes environment. It solves the key problems of the serverless model, which are scalability based on a number of outstanding requests. And very important, the component can be replaced or customized. Because as we have some very specific needs in our platform, and as we want to make the product evolutive during its lifetime, we want to add features, we want to address issues and scalability problems. So we want it to be customized. And moreover, it's written in Go, which is a language we love at Scaleway. So the choice was pretty good on the serverless engine. But to run it, we need a base. And Knative is using Kubernetes as a base for running as a platform. Kubernetes, it's a proven technology. It was used by a lot of people at the time. There is a huge community around this product. It has all the scalability features that we want integrated. But is it a good solution for everyone? Like I said, maintaining an infrastructure is a bit hard. It takes time for people. It takes knowledge. It has a cost also. But guess what? In the Scaleway ecosystem, we have a Kubernetes as a service product. So it was easy for us to deploy. And we also had experts in the company. So in any case, if we had any issue with Kubernetes, we knew who to ask. So it was an obvious choice for us. It was a good choice for us, but still it's not a good choice for everyone. So what's needed to reach the final steps toward the proof of concept? As all Scaleway products, we have a Scaleway API that we want to expose. It's used to give access to the REST API. It's also the component on which we build the other tools like the CLI and stuff. We want some basic isolation. And at that time, we had the namespace isolation included in Kubernetes. And we had the containerd isolation, which is a layer of isolation. The container isolation layer is a bit weak for an industrial solution, and production-ready solution. But at the time, for a proof of concept, it was just sufficient. So by assembling all these components, we had something that worked, and we were happy at the time with the steps and with the result of this proof of concept. Let's do a small focus on the Knative component in case you don't know how it works, and that gives some context. So the clients, it's you, and the request goes to the ingress controller. There is only one square there, but actually there are two components. You have the ingress controller, which is responsible to build the configuration, and you have the ingress, which usually is it's not Istio, it's Envoy. So usually Envoy. And so you have the ingress controller pushing the configuration to Envoy to create all the routes that are used to transport the data. Then you have two cases. When your service is scaled to 0, then the requests are given to the activator, which is a component responsible to feed the information to the autoscaler. The autoscaler then creates or updates the deployment to scale the number of Knative function pods. In the other case, if you already have function pods, then the ingress controller will route the request to the Knative function pods. which is composed of two components, the queue proxy and a user container. In the user container, you get your code. And in the queue proxy container, it's used to queue the requests that are incoming and to feed metrics to the autoscaler to give more insights to it and to give the autoscaler sufficient information for it to scale the deployment to the right size for your workload. So, okay, now we have a proof of concept. I want to push it to the public beta. So what's missing from this proof of concept? There are three key components that we wanted to have on the public beta that we didn't have on the proof of concept. There is the function as a service layer. We want obviously stronger isolation to be unable to onboard external people, external customers to this solution, to this platform. And we want private functions. These were the three main components that we needed at the time. So the function as a service layer, what you need to know is Knative natively has only support for container. So the function as a service part has to be built from us. So in order to build these containers, we have to push the code from the customer to our object storage, and then we have to assemble the image. We're gonna zoom on the image a bit later to understand how it's composed and all this process works. We have to compile the code in case if it's a programming language where you need to compile the code, for example, Go, and then we have to push the container image to the registry. So why do we need all that? And what's in a container image? The container image obviously has the client code, which is what we want to run. We also need library dependencies, which, for example, are the necessary libraries to connect to an external database, which is a classic need when operating code in the serverless environment, because most of the time it's not data is not persistent in the containers. And we have two more components, the core runtime and the intermediate runtime. The core runtime, its mission is to handle the request, to transform it, to translate it to a form that is standard, that is compatible with AWS runtime. And then we have the intermediate runtime, which is a component used to start the client code, but with native language. So let's zoom on these components, on the runtime components. Sorry. And for that, we're gonna inspect the life of a request. So let's see how it works. We have 5 steps during the life of a request. First, to handle the cross-origin resource sharing, which is a mechanism to add some headers in order to be able to use web browsers and to do query from web browsers. So for security, we have an authentication layer. It was the first iteration, and we put the authentication at this point, but really that's something we want to put elsewhere in the future, and we're working on it. Then we have the payload check, which is responsible for transforming the request to a standard format that will be used to invoke client code. So in this new form, in this new object, we have the trigger type, color information like its IP address. We have some header parameters. We have resource information, and also the execution context. So once transformed, this request is transmitted to the sub runtime, and it will invoke the client code, which will in its turn generate a response and then send it back to the client. So there are other components like logging and metrics, which are reported to the customer, so it can see how many queries it has outstanding, have more info on the errors, and the queries and the colors and all that. And it's all integrated in a product, but we had to put it in the runtime so it will share this information and centralize all this information. For the first authentication system, we use GWT, which is also not the best system when thinking back about that, because you have to renew your tokens pretty often. So it's good for some usage, but it's not ideal for all type of usage because it has some constraints. Another problem we had to deal with, like I said, was isolation to handle container security. The problem is, like, you're uploading some code that we don't control, so we have to deal with that. We can't trust the code that the client load on the platform. So what we did is study what we could do to further isolate the workloads, at least a bit more like just containerization. Because containers, they are a great way to isolate things and to constrain performance, but there are security issues. There have been a lot of security issues the last years. So it's not really guaranteed that the isolation is really proper. So we thought at testing different products like gvisor from Google and Kata containers. So gvisor is an interface that filters the system calls. So it can check which parameters you put to the system calls and avoid sensitive calls. Like you can choose which system calls are allowed and which are not. So it adds a layer of security. The other option we had is Kata containers. Kata containers is based on the principle that you can start a micro virtual machine and the containers will be spawned inside this virtual machine. Obviously, we said that the problem is with that is the performance. gvisor runs all in software with no acceleration, so we are not very satisfied with the solution. It had a lot of overhead, and moreover, it didn't enable us to limit the quantity of RAM and the quantity of CPU that is dedicated to each application. Kata container, on the other side, is based on QEMU, so it's got KVM acceleration. So that was the option we took because it was the best trade-off in terms of performance. The KVM acceleration gives us good runtime performance. The only problem with that, it takes some time to start up the virtual machine. So it's a bit of an issue with cold start time, but we have some things to deal with that. So like I said, the drawbacks, performance, overhead, and startup time, and it also adds some architecture complexity because of course you had virtualization into already existing virtualization. It gives some complexity on the network also. And you have to integrate this in your Kubernetes nodes. So it has to be supported on the infrastructure. But that is something that is integrated in your Kubernetes product. So that's also fine. With this, we reached the path to the public beta, and we onboarded a lot of customers who wanted to try the product. But yet, this is not the end of the road, and we want to push the product to general availability. So, in this road to scale, there are so many steps. That's something that surprised us, that there are so many little details that we have to address. For example, setting up the registry, tracking object in database, add metrics and logging, the multi-cluster management, so many things. We're going to see some of them, but it will take too much time to just address all the points. So we're going to see only some interesting points. For example, the ingress controller. I talked about it a bit earlier, and that is a point that we had a lot of problem with. At first, we tried Istio. Istio is a generic ingress controller designed for Kubernetes. And that's what we thought would be a good solution to start with. And it was, but it was a bit complicated. It was a bit bloated at the time. So many features, so many things. So we rapidly hit performance issues because something that we have to understand is when using Knative, it creates and deletes a lot of objects in a Kubernetes cluster at a rapid pace. Because every time you scale your deployment, then you have new container, new pods, start new processes, and this creates and deletes objects in a Kubernetes cluster. Moreover, Istio is using CRDs to describe the services. So it adds a new kind of object in a Kubernetes cluster. But anyway, we try to find other solution and we switched to Contour as a second solution. Contour was way more simple and it did the job pretty well for a long time. But the problem was like Contour is also a generic solution with its own CRD, which is a custom resource definition for those who don't know Kubernetes. Custom resource definition gives you the opportunity to define custom objects that you can put in the cluster. So when you create services, you create these custom objects, and this will create the routes and all the HTTP routing that will give access from the external queries to the internal services inside of your Kubernetes cluster. So it was working pretty well until we had like thousands of services, thousands of functions and container. The problem is we need to support frequent reconfiguration because each time you create new container, new functions, or you scale your deployment, then the configuration of the ingress controller is changing. So yeah, rapidly we reached the limits of Contour on this usage. And we looked at the Knative project and we saw that there was Courier. Courier is an ingress controller that is designed to be simple, efficient, and it's built dedicatedly for Knative. The XDS configuration with this streaming configuration system that you use with Envoy is included, and with no ingress CRD. So it's directly feeding on the object that Knative is using. So dramatically simpler and dramatically more efficient. So it addressed the needs we had to support frequent reconfiguration, updates of many services. And also a point that we loved is that there is a dynamic community around this product. And we already made some merge requests and changes on Courier because, like I said, we reached the limits of the product and we had to add some new features for our needs. And they were very responsive, and there is a very good community around this software. Another thing that we had to design to make it bulletproof is to add cluster sharding. So why cluster sharding? The first need is horizontal scaling, because you cannot just have one Kubernetes cluster. There will be too many services, too many pods, too many everything. So we had to use many clusters in order to achieve infinite scaling. Sorry. The other advantages that it brings is you get further isolation of workload. Obviously, if your workload are running on different Kubernetes cluster, then they are isolated one from another. Also, it gives a smaller blast radius in case the cluster has an issue, then it doesn't apply on the other clusters. And for the horizontal scaling, we used one of the simplest mechanisms that exists, which is DNS. So each service points to a different cluster, and that's something that we control. And we will see that using this approach of cluster sharding gives other advantage to our infrastructure. The thing is, now that we learn to shard the workloads on different clusters, we had to create tools to migrate workloads from one cluster to another. And the advantage of this is that all the new features that we develop can be put on new clusters. So every time we have something to test, a new feature in beta, then we can put it on a really different cluster and migrate the clients that are willing to test this new feature without disturbing the other ones that are running on production. Moreover, when we have to update the core components, like a new major Kubernetes version or new major Knative version, then we can ensure that the new cluster is ready, up and running, and strong enough to handle production workloads before migrating any customer needs. So we actually never upgrade an existing cluster. At all time, we create new clusters, we migrate the workloads, and then once we know that everything is migrated, we can remove the old cluster. And that enable interruption-less migration and upgrades. And like I said, it's very good for canary testing and easier beta testing. One of the steps that we want to reach also is further strengthening our system to face external threats. So we added more network policies to further isolate workloads one from another at the network level. Because inside a Kubernetes cluster, by default, you can have access to all the pods that run in this cluster, at least in the namespace. So we added some restriction about that. We also added rate limiting because we have large clusters, but they have their limits. So we needed to ensure the number of requests that are coming are able to be handled by the cluster. So the rate limiting is pretty high, but it's just to avoid denial of service. And also we had to add resource quotas because we do not want one customer to be able to consume all the resources in a cluster. One of the pillars that we relied upon when creating this service is to test, and test again. So at each step in our software and in the infrastructure that we deploy, we do some unit testing, integration test, end-to-end test. We onboard beta tester for each new feature, and we do some regular health checking, functional monitoring, and performance benchmark. Benchmarks are done regularly on the different cluster because these are some workload that the cluster is supposed to be able to deal with. And we have functional monitoring. So we put ourselves in the shoes of the user, try to deploy services, try to query the service and see how it works in the duration of the request, the responsiveness of the systems. So we get some really good insight on how our systems are working. The thing is, we can't just observe. We do it. We can just observe the workloads from the customers because we do not have access to the code. So we don't know what's working. And for example, when there are errors in the customer code and we get like some 500 errors, then we're not able to really know if the error comes from the customer code or from another issue in the system. So with the functional monitoring, we can ensure that this is code that we master. And so we can have really good insights on how the system is working. The last step was to integrate this into the Scaleway ecosystem. So of course, we have a lot of services around the products. We have the billing in order to be able to earn some money from the service, of course. We have the trust and safety, which is used to track abusers, which is also a service that people use to complain about misuse of Scaleway systems. It's also integrated in our central authentication system, in the console, in the dev tools. Yes, the developer tools are very important because it's really part of the developer experience, which is key for developing a serverless system. We have the CLI, which is provided for all our products. And we integrate with third-party tools like the Serverless framework, which is the most used tool in the serverless community, and Terraform, which is also very popular to deploy services. So yeah, hooray, we reached general availability. But what did we learn during this journey? Something that was a bit surprising is the difference between function and containers. We thought this as really similar products, but there are really different use cases and interactions. So the most obvious difference is it's for function, the runtime is included and provided by us. For containers, the runtime is brought by the customer. Functions are more designed for very simple tasks, and it's a great tool for that. For containers, it's more flexible, but it's a bit more complex for our customer to use. Functions are easy to use, whereas containers require more knowledge to operate, but are more flexible, like I said. For the billing part, we chose to differentiate the two products, and that's one of the main differences in our systems. For function, we are billing per request because we can really measure how many requests are made at a time, because we have one for each container that runs functions. For container, the customer can choose how many requests a container we handle horizontally, so it's built per runtime, enabling people to handle workloads that are running for more time. Other things that we did learn is there are a huge difference between homemade and industrial. So that's something we thought at first, but there are so many little details to put and to handle, and this was the part where it was a bit surprising. Do we regret using Cube and Knative? That was a strong choice that we did at first. By looking back, no, we don't regret using Cube and Knative. So the choice was good because Knative is a very good product. All the doubts that we could have about like customization, the ability to deal with the large workloads, then we were very happy with that. Kubernetes is a very great tool once you get to know it and once you get to master all the internals, how it works, very interesting. And it comes with a lot of tools, observability, debugging, so a very good base. And that is something that we won't have if we created a product from scratch. So like I said, customization was a key to success. And the fact that Cube and Knative were very customizable, it was something that was crucial when creating the service. Still, we have lots of improvement yet to build. We want to add some more tooling, new features, improve the developer experience further. So yeah, what's next? Like I said, we want to focus on developer experience because that is a key of success for this kind of product. It's all about simplifying the workflow, focusing on the code, having something that just flows, having something that is easy to use, where you get a lot of metrics, a lot of control, despite just not dealing with the infrastructure. We want to continue expand the serverless ecosystems because it's not just a product, it's a pattern. So we want to provide other databases, other tools, other products around the serverless ecosystems to make it more complete, feature-rich, and to further increase the possibilities that people will have by using the systems. And we still want to continue promote open systems because that was really a success. Using open source components, we did a lot of merge requests on the projects, and the communities were so welcoming, so nice with us, and very responsive to all the needs around that. And that's the end of my presentation. Thank you all. And if you want to be part of a journey, we are also hiring a lot of people these days. So don't hesitate to visit our career website. Thank you all. I hope the presentation was interesting for you.
Okay. Thank you. Thank you, Nicolas. Do the people in the room have any question? No question. I don't see any question online, so thank you, Nicolas, for your time.
One question. In which time frame was this done? So when you started from scratch and did all this technology evaluation, let's say how much manpower or how long did you work on this until you say, okay, it's time for a public beta or something like this?
Okay, so the question is how long did it take for us to build the product and how many men were involved? But maybe the question is more about the from the proof of concept to the public beta.
So you want me to answer the question or do you want to answer it, Lucas?
No, please answer it.
Yeah, okay. So we're a team of 3 to 5 developers that each changed a bit during the whole project. It's a bit hard to find people who have the deep knowledge of Kubernetes and all these products. But yeah, let's count 3 to 5 people for 2-3 years, and we are continuing to develop the product still today.
Thanks.
For more precision, the longer part was the road to the industrialization, because setting up the POC took us less than 6 months. Last 6 months to go to public beta, and then all the improvement after took 1 year and a half. That's the longest and tougher part, to have the service up and running to serve clients.
Yes, as usual, it follows the 80-20 rule. So you can do 80% of the product in 20% of the time, and all the details, all the subtle things that takes so much time.
Okay, thank you everybody, and if you want to discuss with me or Nicolas, you can contact us on LinkedIn or using our Slack channel. We are always available. Thank you.